Yeah, I've just selected it.
Started. Now let me see if it shows up on my.
I mean, you would have to activate it still in your you have to go live in the YouTube channel.
Well, it's already there. So
oh, I see.
So it's actually doing it. I mean, I had already set that up. So
okay.
So right. So I would say just leave it on and turn it off when you're done, Mark. My meeting is going to be an hour, so I'll be back around. Guys are doing 4:30. And Mark, I'll let you set up click record when you're ready to go, which will be in the next few minutes. But so I think everything's okay. And now you can actually make people co-hosts if they want to write. Okay.
Yeah.
So I'm gonna do. Mark's the one in charge. Okay?
Yeah, it's streaming to YouTube. Okay. I think.
Yeah. Great. Very good. We're all set.
Perfect.
I'll be back. Like I said, shortly after 4 o'clock.
Okay. Thanks, Robert. So maybe there's a few minutes until we reach 3, so we'll wait till that stage.
You're leading this thing with Maxim, Richard?
Yeah, I'm good. We'll see out.
Great.
My plan is to follow.
Okay.
Do you remember many years ago when Atiyah made us lead a discussion session on Hodge theory? And I basically didn't know what it was, so you had to do everything.
And Kevin Costello was in the audience, which made it, yeah, he knew a lot more than us. We should have just made him do it.
Yeah, absolutely.
Okay, well, 3 o'clock Eastern time now, so I'm just here to do things purely on the admin side. So Richard and Maxime will be leading the discussion. We're streaming to YouTube. We'll be recording this on Zoom. We can decide afterwards whether or not it's something that people are comfortable having on the collaboration website in posterity, but at the moment, Richard and Maxime are co-hosts, so they can write on whiteboards.
Okay, maybe I'll share screen. Yeah, just a second.
If
it will take
at some stage somebody else has something that they would like to share and everyone agrees, then let me know and I can make them co-host.
Okay. Yeah, okay, so probably I hope you see white page. Yes, suppose. Yeah.
Yes.
Okay. Yeah. Maybe there is something which I want to start from. Is it some perspective on wall crossing, which is kind of not presented in program of the conference? There are actually two things which with Jan we developed. It's already several years. Yeah, a perspective on wall crossing through Foucault categories and kind of new type of, one can say, mirror symmetry. Maybe I'll briefly explain what we have in mind. Yeah, so I will just write on this things. Yeah, so we start with holomorphic symplectic manifold. Actually, it will be algebraic symplectic manifold. And not anything works. It should be something like convex at infinity. And I'll try to think of manifold like cotangent bundle. Maybe just a second. Let's change notation. So denoted by M. So examples one can have in mind, it's M is cotangent bundle to algebraic variety. Actually any dimension. Then you can imagine M will be C star to power 2n with some of dxi, xi in such symplectic form. Or you can imagine something more interesting like I'll just draw a two-dimensional example. Elliptic curve multiplied by C star. And two form will be one form on elliptic curve, non-vanishing one form elliptic form times d log of coordinates on C star. On E multiplied by dx of x, like this. Okay, so there are various examples. One can also go to actually closed manifold like case resurface. But we mostly stay in examples 1 to 3. In example 3, it's not a fine variety, but one can make little modification. You can make 3 prime and will be CP2 minus cubic curve. And you consider two form which has first order pole along cubic curve. It will be a fine variety, like example 1 and 2, if X is affine. Yeah, so I get various types of algebraic symplectic manifolds. Yeah, we kind of really understand quite well situation when complex dimension of M is 2. It's kind of really best case and essentially reduced to this cotangent bundle to curve or stuff like this. And here we hope we can formulate things really, really rigorously. And in high dimensions, it's purely hypothetical. But the whole picture works in any dimension. And you see in dimension 2, one can try to relate it to stability in 3 Calabi-Yau categories. But in high dimensions, I don't see room for 3 Calabi-Yau categories at all. So for general perspective, we want to really go from 3 Calabi-Yau categories. Yeah, so sorry, no, for stability conditions, usually Donaldson-Thomas invariance when it's 3 Calabi-Yau. And here will be no 3 Calabi-Yau category perspective in general, unless dimension of M is 2. And what I want to add here, if you have M, such M, then it's usually gives a analytic family of, let's say M is affine, yeah, of associative algebras, depending on some parameters, which it's not one parameter family. It's one can make one parameter family, canonical one parameter family, but it's in general, if I'm where I am, it will be high dimensional family. Yeah, so it will be like differential operators. M is cotangent bundle to X will be algebraic differential operators. Or you get C star square, say, you get, you write quantum torus.
You stopped sharing. I don't see anything.
Oh, it's I don't know why. No, I didn't stop.
Yeah. No, I think you.
Okay, now it's back.
focus on the window.
Ah, yeah, yeah.
Good
Okay,
now.
it's maybe okay. I understand.
Everything is good now.
It's good, yeah. Yeah, you get quantum torus and you get variables kind of invertible, you get Q difference equations, and yeah, you see it will be in some kind of parameter H bar here, say, and it's not really algebraic family because it depends on exponent of H bar algebraically, but not on H bar. And if you get elliptic curve, you get something like Sklenin algebras. You consider CP2 minus elliptic curve cubic. And you put right parameters. Yeah, so you get natural algebraic quantizations. Now we want to relate two things. Yeah, but before going on, one have to make certain choice. One should embed m omega to some Poisson variety. So it will be symplectic leaf. And Poisson variety will be not compact, it will be partial compactification. There are very few examples when it's really compact. And what we want to put here, we get kind of log Poisson structure. There are many meanings here. And what do I mean by log Poisson structure? Is that kind of symplectic form, as meromorphic symplectic form, looks in local coordinates as sum over dxi over xi times dyi. Xi maybe close to 0, not close to 0. Yeah, so it will be such kind of behavior. Yeah, especially nice in dimension 2. I don't have choice, it will be just divisors. Yeah, such things it's almost never compact. For example, if you start M is cotangent bundle to a curve, so you see that this Poisson compactification will be cotangent bundle plus P minus M will be union of some finite union of copies of C. Oh, roughly. Yeah, oh, in this case, it's really C. It will be disjoint affine lines. Maybe I'll just replace it by affine lines. It will be disjoint union. And such things correspond to what? Yeah, it's actually, they correspond to various points on your curve and various exponential terms for singular for solutions of differential equations at this point. With the exponentials times some piezo polynomial and inverse variables. Yeah, so you get cotangent bundle and you add few this A1s at infinity. There are all, if you want to break, you get only finitely many, and they get add more and more. And if you have maybe M will be C star square, then all log divisors will be the same as rational rays in Q square or Z square. So it will be all toric divisors for this open torus. And if we get M elliptic curves times C star, we get just E times 0 and E times infinity. Just get two of them. And in this case, compactification will be compact, will be E times CP1. Or you get CP2 minus cubic curve will be only one cubic curve. Yeah, so there's, you get this choice of divisors which you glue to infinity in dimension 2. In high dimensions, we really don't understand it well. And let's stick to 2 dimensions. So you get M sitting in this partial compactification. And it leads to 2 kind of categories, 2 A infinity categories. Namely, the first one we consider Foucault category of M with as a real manifold with symplectic form will be re omega to 0. And we'll get B field, which will be I times imaginary part omega to 0. And if you like, we can add to B field also some torsion B field. Yeah, And what you consider object, kind of Lagrangians or something, such, oops, probably disappears. Yeah, such that is sitting in M, such that closure of L sitting in P is compact. So it goes to infinity in direction to this partial compactification. And you consider kind of wrapped Foucault. You start to move things going to infinity freely. So you get something. You get category, and maybe I'll call it kind of Foucault holonomic of M, maybe with P, with this compactification. And another things you consider quantized algebra, which I didn't denote anyhow. It depends on, and you put this parameter 1. This parameter 1 can think it's like rescaling of your form. One can also put here one edge bar if one want to put one complex parameter. So you have analytic family of algebras, and for these algebras consider holonomic modules, which became in a sense compact when you compactified by P. The category of all modules of quantized algebra, one can, it's kind of deformation of category of coherent sheaf on M. And one can define something like coherent sheaves on P, and then quantize coherent sheaves on P. And holonomic modules will be object with compact support on this quantized things. It's easy to define. Yeah, so you get two categories, and then general conjecture, the equivalent. And yeah, if you take again cotangent bundles, then Foucault category, it will be some kind of local systems, maybe regular local systems. And when quantized modules, you get D modules, bundles with connection with prescribed singularities. So it will be Riemann-Hilbert correspondence. And
are you saying that these two categories are equivalent for the same M and P?
It's the same M and P, yeah.
So there's not a mirror M and P.
No. It just gets the same manifold, but you have kind of two completely different descriptions. One is Foucault-like description when you use holomorphic disk and so on, and another it's using some kind of algebra. But it's really the same variety.
Yeah, but since it's complex symplectic, it's rather should be compared with mirror symmetry for hyperkähler, if you'd like.
No, I don't want. No, I don't want to compare.
No, I'm just.
There's no XYZ aberrations here whatsoever. That's the point.
Yeah, and it's not mirror symmetry. So first.
Yeah, it's kind of analog of mirror symmetry. It's a new statement, not terribly well formulated, but just maybe three types of examples, and we check by different tools in these examples it works. Yeah, for example, consider C star cross C star, consider some Q difference equations, and then I get identification of Q difference equations with, again, some kind of Foucault category. It follows from some result by Ramis and his collaborators. So it's I have really no idea how to formulate and prove it in great generality, but in examples one can do it.
Can you say a little bit more about the holonomic modules? Are these modules with, for example, before you deform into the non-commutative, what are these coherent sheaves?
Before deforming, it will be the following guy. You consider coherent sheaves on P, whose support is compact, with compact support. And then on this...
okay.
Yeah, but then you get too many things. You get like skyscraper sheaves, yeah? And then this is actually abelian category. One can put some stability structure, and then one can extract certain right abelian category inside by some slope condition, which will guarantee that supports will be Lagrangian, exactly Lagrangian.
And the holomorphic symplectic form is used in order to define the stability condition?
It's the same. Yeah, I don't use scalar form at all here. One can use it, but I don't do it. Yeah. So that's That's the picture. Okay, well, one can check many examples, but now what one can do with this? So I will skip my Poisson variety from notations. So I get my symplectic manifold with re omega to 0 plus I imaginary to 0. Yeah, this will be symplectic form and B field. I treat it as a real manifold. Now, suppose I have a Lagrangian manifold, actually Lagrangian analytic subset. And such that closure of L in P is compact. L could be very singular. It will be like union of, it could be arbitrary, it will be actual algebraic maybe subset because I do algebraic varieties. Lagrangian algebraic subset. Closed algebraic subset. Yeah, so I get this Lagrangian guy. And now the story is the following. So the picture is that if we have this Lagrangian guy, then we can associate a local Foucault category. Which doesn't depend on the whole manifold M itself. Or roughly speaking, what you get this L, whatever, this like union of two curves. You take its small tubular neighborhood, which will be Weinstein and also going a little bit to infinity. And then you consider, again, like object going to infinity and make a little bit of wrapping. Yeah, so I get this category from, and there are some better understanding of this category with by work with, I think, Schende and Pardon. Yeah, one can have actually local shift. It's actually defined locally. One can have certain local notion of at germ of each point of this category. It will be constructible shift and get something like global sections. And if L is smooth, it's just usual local systems. But if L is non-smooth, will be something going on in singularity. Yeah, so this is a local category, and in general, Foucault category, it's big Foucault. This is combinatorial objects is defined over integers, say, okay. And big Foucault category, it's something tricky. But if, oh, sorry, I think it disappears. If I consider integral of omega of all homology classes, which will be H2 of ML Z. In fact, H2 can be replaced by pi 2. If all integrals do not belong to positive integers of holomorphic to form, I claim that this local category is embedded as a full subcategory to Foucault category of M.
Positive integers or positive real numbers?
Integrals, no, integrals are not, don't belong to positive integers, yeah.
You just wrote R instead of Z.
No. I consider homology classes which integer coefficients, so I get a lattice of finite rank. And the conditions that when I take all integrals of my holomorphic to zero forms, they do not lie on real positive real ray. Why it is so? Why this category should be part of full embedding? In fact, it belongs to kind of real symplectic geometry. If you get a real symplectic manifold with arbitrary B field, and you take Lagrangian closed Lagrangian subset sufficiently nice, so it can have local Foucault category. And then we expect this local Foucault category is perturbed by holomorphic disks, yeah, with boundary on L. even for singular Lagrangian subvariety. And in our special situation, when I get holomorphic complex structure, I can use almost complex structure kind of pointwise, pretending that it's a hyperkähler manifold. It will be not integrable in general. I don't care, but for this almost complex structure, it's easy to see that any holomorphic disk in this new almost complex structure will have automatically vanishing on its imaginary part omega to 0 will be vanish automatically, and the real part of omega to 0 will positive automatically. So the integral will be a positive number. But this is pure cohomological condition, so we don't really care what kind of almost complex structure we choose. So we get this kind of well-defined, fully faithful embedding of this category. And now how we understand trivial crossing from this perspective, now we change parameters, like multiply omega to 0, divide omega to 0 by Planck constant, which will be complex parameter. And then move your Lagrangian subset, or even change complex structure of M and L together. Yeah, so you get many parameters to change. And then it will be real hyper surfaces when this cohomological condition fails. We don't have full embedding. So what happens, you get kind of parameters of everything. Like H bar, for example, you get omega to 0 over H bar. And you move L, M, you can deform everything. And parameters of everything consists a lot of real hypersurfaces on which this local Foucault category of L is not fully embedded to Foucault category of M. But in this parameter space, you have kind of 2 points, kind of plus and minus point. You get still two embeddings if you move a little bit from on this hypersurface on one of sides on the other side. And then you get 2 full embeddings. And if you go to limit, they will differ by certain, they will be slightly different. We get automorphism of this local Foucault category, depending on my omega to 0, and this automorphism will embed this areas of holomorphic disks. So it will be certain series of certain periods, 1 over H bar of certain periods. Yeah, it will be over some Novikov ring related to these periods. And here we get exactly real numbers divided by H bar. So that's the rough picture. You get this automorphisms of categories, and you can introduce, say, what is automorphism categories in more and more concrete terms, like you get modulus space of objects, introduce some coordinates. For example, consider if Lagrangian manifold is smooth.
I don't understand what the automorphism is doing.
You get kind of 2 embeddings which I defined only at the limit if you change a little bit your parameters to one side of the wall or another side of the wall. You got 2 full
embeddings. The automorphism to be an automorphism of the target F of M.
No. It will be automorphism of. It will be embeddings. You see, it's full subcategory. It's like you will get essentially the same objects, but you parameterize them differently.
Okay. I mean, so the full subcategory of F of M is the same.
Yes, yeah.
On both sides,
the same,
but the identification is different.
Yes, that's the point. Yeah.
Okay.
Yeah, you get canonical automorphism of this category. Yeah, actually, it was in fact in other circumstances. This was first wall crossing which we observed in a very old K3 paper with Jan when we construct. We are doing more or less real symplectic geometry, not complex symplectic geometry.
Sorry, Maxim, can you explain what the e to the minus 1 over H bar is? What's that saying?
Because this automorphism, when you write a formula, it will be certain sum over disks. So this automorphism will depend only on holomorphic disk is boundary on L. And for this holomorphic disk, we should keep track of them with the weight exponent minus 1 over h bar omega. And it will be exponent minus small real number when h bar goes to 0. Yeah, it will be, yeah, that's roughly the picture. And yeah, that, for example, it gives automorphism of moduli space of object. And if L is, let's say, smooth variety, then one-dimensional local systems are perfectly object of F local. If they form a torus, algebraic torus, and you get, depending on small parameter, automorphism of this kind of analytically automorphism of this torus. That's the usual for Duval crossing. When consider moduli space of objects, moduli of rank 1 local systems, you get tori, it's B1 of L, and you get as automorphism, you get for Duval crossing. But now if you do, for example, you can imagine your variety, it will be union of two, maybe two smooth manifold. Let's intersecting its few points. Then if consider Foucault category of L, it contains, because it's by shift property, contains Foucault category local of L1, Foucault category of local of L2. You get local system on Val, local system on L2. So if you don't have 4D walls, you parameterize nicely object on the large Foucault category. But now if you want to parameterize Holmes, because Holmes will be correspond to intersection points, and then you get other abstractions like holomorphic disk with boundary on union for L1 and L2. And this will be kind of like mixture of 2D and 4D wall crossing. Yeah, so it's all explains very neatly. So we get this wall crossing, we get changes of coordinates on moduli spaces, or maybe on Holmes, whatever. And then we expect it should be analytic wall crossing structure. In sense which I explained yesterday. And then it should glue this nice kind of like second construction and make cuts and glues, glue new analytic family. And this analytic family gives rise to resurgence and or formal power series. Everything should be trivialized, and this should go to deformation quantization, which I proved many years ago. So it really combines many things. This picture combines deformation quantizations, algebraic deformation quantization, this wall crossings, and resurgence, and it gives kind of one consistent pictures of all various quantizations. And if you apply, for example, to C star square and take nice, what's called K2 Lagrangian varieties, then it should get more or less complex Chern-Simons theory. So it's so already it's kind of like universal picture related to kind of two-dimensional field theory. It's kind of responsible for things in many in arbitrary dimensions. And I don't see three Calabi-Yaos in this story at all, I have to say. Yes, that's one point, and there is another point which I don't really want to talk much about it. Another viewpoint, it's more recent. It's actually reduced to one-dimensional field theory, not two-dimensional QFT, but one-dimensional QFT. And the story is that you get this various resurgence series and so on, how to understand this whole story. Suppose you get just two Lagrangian manifolds, L2, L1, and M. Algebraic Lagrangian manifolds, and I want to have certain eventually resurgent functions and actual functions, get actual numbers by Borel summations. So you get actual numbers from Borel summations, and the rough idea is that one can interpret in different way, consider space of paths. You consider all maps from 0, 1 to M is, so it's a bit stupid with notation. If you consider this F0 x and L1, F1 plus L2, and you integrate exponent of what I roughly integrate PDQ, kind of d minus 1 of omega. Consider this, you get this topological field theory. It's really not well defined. It's defined maybe up to constant. You get multivalued function space of paths, and you can try to make sense of integrals and integrate over Lefschetz Timbals, where fixed critical points are just constant maps to intersection points. So you get this story, and you want to make sense of this integral, and eventually it will be some kind of reformulation of what I talked to you, but with this perspective of infinite dimensional holomorphic Morse theory. So that's counting of holomorphic disks will be replaced by counting of gradient lines for critical points for the section. That's essentially one story. And but this second story, it's actually more general, much more general. For this action PDQ, it's just reshuffling the picture which I told you before about this interaction of various quantizations and Fukaya formal quantization and algebraic quantizations. But here, what one can add here, one can add also some Hamiltonian depending on time. And this also should, it's a bit long story, it's also get new resurgent series, but with much more complicated behavior. So if you consider it will be not just lattice affine rank which is mapped to Z, but really something of infinite rank. Because when consider critical points of the thing, it will be solutions of some ODE like geodesics in complexified varieties, so things like this. You get infinitely many of them, and it's a kind of brand new class of resurgent functions, well beyond this previous picture with Fukaya categories. Okay, so I think it's I'll just give you some. I think what we are thinking with Jan last already maybe 5 years or more. Do you remember?
For this second viewpoint, do you see a connection with this old work of Hingston and Bott about loop space, cohomology of loop spaces?
It's not cohomology. It's actually more interesting. It's you get not cohomological information, but actual integrals which you cannot reduce to naively to some cohomology. For example, one of things which if you add a non-trivial action, you get you get things like exponent minus h Laplacian, things like this, like trace, or such things you can express in this path integrals, and the claim that such traces or even matrix coefficients of this for h bar goes to 0 will be resurgent series, which is a new statement. But it and here there's no Fukaya categories, at least naively. Okay. Yeah. So it's kind of a bit opposite to what Greg Moore explains: the 6-dimensional series, 4-dimensional series, and I go to 2 dimensions, even to 1-dimensional series. Not trivialize basic things. Yeah. Okay.
Can you explain how the different local Fukaya categories for different Lagrangians are related to the whole? How are they?
No. For each Lagrangian, they're embedded. But if you have 2 Lagrangians, you can make the union. It will be very bad. It will be singular, but it will contain the full subcategory for categories for both of them.
Yeah, the thing is that if you define the local Fukaya category, your Lagrangian doesn't have to be smooth. So you
not necessary. It's just
you
complex
take just
analytic.
a neighborhood, like Liouville neighborhood.
I'm wondering if there is some sense in which you can choose a selection of Lagrangians, like a finite set, which will generate when you embed the local category.
It's maybe okay, but if you want to consider limits when h bars goes to 0, then the limit will be some kind of like Higgs field. It will be coherent sheaf. It will have certain support. So,
I mean, but very naively, you can imagine that there is just one skeleton which generates everything, but it's a very, very naive picture.
Yeah. The story is that also from Fukaya categories, one can use some non-holomorphic Lagrangians, and it's really quite interesting. For example, if one try to think about, maybe I just go next page. Yeah, if your manifold is just C2n, yeah, okay, like cotangent bundle to Cn, yeah. One can imagine again like algebraic Lagrangian submanifolds, yeah, and that should give nice circumstances as holomorphic modules and so on. But also one consider R2n, Ctk M. Yeah, when I have appropriate like Planck constant will be imaginary, say, when I get this R2n, it's also Lagrangian. And when I try to think what are homes between holonomic D-modules and R2n, it will be very nice. It will be solutions of holonomic D-modules in Schwarz spaces. Yeah. So this R2n, notion of Schwarz space.
Can you explain that?
Yeah. Okay. Yeah. For example, you have some differential operator. Yeah, you get something like h dx square plus whatever. You get this. For example, you get some, like in one variable, so consider a differential operator equation depending on our parameter. Get d module. Yeah. It gives you certain. You get spectral curve. Yeah. In C square. And now
degenerating as h bar goes to 0, you're saying.
Yeah, and if consider intersection with R2, I claim this number of intersection points, it's not topological invariant anymore. Yeah, it's and this will correspond to solutions of your equations with complex coefficients on R, which have at most polynomial growth at infinity, so it will be like in Schwarz space. Yeah, it's really interacts nicely with kind of Stokes phenomena, because you have solutions with exponential growth, and you consider solutions without exponential growth, only with exponential decay along real line.
In the first case, you were studying Schrodinger equation on the affine line, a complex one-dimensional variety. And in the second case, you're considering it on R. But
yeah, you just restrict it on R.
Yes.
And you're interested whether you get solutions of your equations which are don't increase. And typically, there will be just exponential decay in both ends. Yeah.
And so the Hom space would consist of that dimension, the space of solutions.
Yes. You see, because these things are one complex, another is real. This Maslov index are not the same. For complex varieties, the mathematical syntax is the same. It's kind of maximal, get maybe x1. But here it should give x0 at x1. So you get certain complex. And this complex will calculate kernel if you operate in Schwarz space. Yeah, but it's really showing off. It's nothing related to. This is not related to resurgence at all. Why I mentioned it, having this totally real submanifold, because it's maybe a direction to prove conjecture of Kapustin-Witten. Because there is still another story for real symplectic manifold. Manifold, maybe Y.
Do you mean Kapustin or do you mean Gukov?
Oh, sorry, Gukov-Witten, yeah. It's not Gukov-Witten. Yeah, because Gukov-Witten proposed there is still another quantization. It's called geometric quantization. Yeah, we want to have Hilbert space associated to real symplectic manifold. And the idea is that it's to have this construction, this real symplectic manifold should be fixed point under anti-holomorphic involution of some complex symplectic manifold. And then you should consider something like Holmes from big brain from M, like all differential operators to this R to N. And from my perspective, you get maybe not L2, but Schwarz space, and then you should get L2 norm as again some composition in Foucault categories and complete it to get Hilbert space. Yeah, so that's the picture. Yeah, so hopefully at the very end we'll see all various quantizations talking to each other in a nice way. Okay, so maybe I'll stop my bumbling. Okay, maybe I'll stop here because.
This reminds me of something. If you have two complex Lagrangians, possibly with local systems, which intersect, not necessarily in a nice way, you can build a perverse sheaf on their intersection. You can take its hypercohomology, and that's a kind of approximation to the Floer homology.
Yes.
But,
yeah, definitely. If you take disjoint union, if union of these two Lagrangians, you get two objects and consider Holmes in local Foucault category, you get exactly this.
Yeah, but if you vary the Lagrangians holomorphically, the hypercohomology doesn't vary nicely in families.
Yes, it can jump. Yeah, they form again some kind of constructible sheaf, I suppose. Yeah.
And I think maybe these automorphisms which you're looking at are what you need to kind of glue along.
For some families, yeah.
In order to make the family of hypercohomologies actually locally trivial.
Yeah. One can also put Lagrange manifolds in families. Yeah, it's true. Yeah, we didn't thought about it. Carefully. Actually, one of kind of picture, maybe formulas which we have with Jan is the following here: that if you have cotangent bundle to manifold, it kind of fibered. You get some L1 sitting in cotangent bundle, but L2 will be cotangent fiber at some point X. It will be vertical. I know. I got one. Of course, this form a local system when X. This base point. It's local system outside maybe some divisors and get constructible sheaf. And this will be Riemann-Hilbert correspondence because if L1 is kind of okay object. There's no obstruction. L2 is always okay object. There's no obstruction as well. And when you consider Holmes, you get like Riemann-Hilbert response, what will be constructible sheaf corresponding to your D module in usual picture, and people want to understand constructible sheaves not through Foucault categories, but through constructible sheaves on the base. Yeah,
but is what you're describing now part of what you did? So you would have to partially compactify and use local.
Yes. No, the trouble here is this partial compactification. It's actually not terribly okay. Yeah, because when partial compactify, you choose X. You consider like a family of partial compactifications.
I think it's kind of an intuitive picture. It's like, I don't know, like meromorphic differential equation, like D module with irregular singularities on the line. And then everything is very, very intuitive.
Yeah. Actually, there is really nice thing story, which I like very much. If you consider cotangent bundle, then omega is differential of one form, which is of one form, like PDQ, It's exact manifold. And suppose L is also exact. So it means that PDQ restricted to L, it will be differential of some function. I don't assume that L is smooth even. It could be very singular. Then what? First approximation, we can assume that L is smooth. The claim that the cell will be absolutely canonical object. There will be no wall crossing for model space of, like, consider trivial bundle. Trivial local system will be no holomorphic disk at all. All integrals will vanish because of this exactness. And then you should get kind of absolutely canonical, kind of God-given D module, depending on H bar, associated to L. And it's really very interesting story. I tried to look on this exact Lagrangian manifolds in, let's say, in C square in the plane. The only thing which I was able to find will be rational curves. I wasn't able to find curve of higher genus, which is exact, which is pretty clean, nice equation in algebraic geometry. And again, using, if one go back, one can really reconstruct from Riemann-Hilbert correspondence what will be your constructible sheaf, or maybe irregular constructible sheaf. The whole the scattering dynamic will be finite. Will be only finite many things, no infinite objects here. And yes, I just want to popularize. It's a very interesting question of algebraic geometry to have this exact varieties. Even singular varieties in plane, which I was able to find, were again curves of genus 0 in some sense.
So, but if you're working with this holomorphic cotangent bundle, and you're considering these exact Lagrangians, so these are not necessarily holomorphic, right?
No, holomorphic. No, sorry, consider holomorphic, algebraic. Everything is algebraic.
Okay, but in that case, I mean, does this fit into the formalism you explained before, where you do have these automorphisms of the local Foucault categories? Or
no, the claims will be automorphism will be trivial because there's no holomorphic disk, whatever argument of H bar.
So all of the local Foucault categories would embed, and
yes, for example, all local, if it's for example, I have this example again on a plane L will curve of genus 0. It will be P1 with many punctures, not just one puncture. And then you get plenty of local systems of higher rank, and they all embed canonically to Foucault categories and D modules. Yeah, there's no corrections at all in this case.
But in principle, you could have non-holomorphic Lagrangians in this example, right?
No, I can have non-holomorphic, but for non-holomorphic, this is all arguments, I think, breaks. No, maybe I'm not. You see, for non-holomorphic Lagrangians, I have I can have non-holomorphic Lagrangians, but this disks for rotated almost complex structure, which spoil me the full embedding, they are not controlled cohomologically anymore. It really depends on the choice of almost complex structure. Only for holomorphic Lagrangians it doesn't depend. If I'm yes, because if you have holomorphic Lagrangian, it will be Lagrangian for what I'm talking about. Maybe I'm wrong. Oh no, I'm not wrong, because if it's not holomorphic, then integral of omega to 0. A second, what I really mean? You need omega to 0 as a whole form vanishing on Lagrangian. It's not only real part.
Real and complex parts.
Yeah. Actually, it's interesting. It's in high dimensions, definitely much weaker conditions than to be just complex Lagrangian. Yeah, so it's opens some perspective here. What can make? Yeah, you're right. Some non-holomorphic object Lagrangian can work.
Can you give an example of these automorphisms of the local Fukaya?
Sorry, example of local Fukaya?
An example of the automorphism that you get of the local Fukaya.
No, the typical automorphism is the following. If L is a curve, complex curve.
Make your screen visible.
Yes. Suppose L is a complex curve in like C2, yeah, something like this, yeah. Get complex curve, and then so it's topologically surface, yeah. Some kind of surface, and then imagine that for kind of bad argument of H bar, you get some holomorphic disk with boundary some loop, yeah. You get a simple loop, and then this loop gives you automorphism of a kind of group ring of the fundamental group. Roughly, it's you get den twist, yeah, about the loop, and roughly, if you have this thing is some curve, it goes to something like this minus this, and you multiply this rotated guy by exponent minus area of the disk. Now one can make automorphism of the kind of lift automorphisms of quantum torus, even to quantum torus, whatever, to automorphism more or less of a group ring of, let's say, free algebra. If my curve isn't compact, fundamental group is free group. I don't remember exact formulas, but it's roughly the same formulas like for usual cluster transformations, but variables and free variables.
The torus, it's a simple cluster. Like X goes.
Yes. There is a story of kind of non-commutative cluster transformations, which kind of parallelly we developed with Sasha Goncharov years ago. We still didn't finish. Already several years we have a text, and then also Berenstein and Retach also had kind of more formal algebraic story. We have really,
so you said that this phenomenon, you said that this category, that this Fukaya category approach, there's this other approach where you deform, you have the non-commutative algebra, and then you look at holonomic modules or some form of subcategory.
Yes.
Does this automorphism phenomenon, is it visible there too? Do you have some way?
No, not at all. No. No, the story is that
story, you don't see at the level of differential equations until you go to solutions.
Yeah. If you fix this kind of Lagrangian manifold, you get many embeddings, and then you start to make rays and apply automorphism, glue a new analytic family, and they claim this analytic family will be exactly this analytic family from which coming from algebraic analytic family of algebras. That's the point. Yeah, and also kind of one perspective one can try to see that if you consider Lagrangian manifold, you get this full embedding Foucault categories. What you get, it's one can interpret kind of like open domain in modular space of object of Foucault of the big variety. So if you move your Lagrangian continuously, it will be more or less the same open domain.
Also, you can kind of think of this bigger category of all, not necessarily holonomic, but all the modules.
Yes.
The category of coisotropic brains.
Yes. We also have story about coisotropic brains, but it's more complicated game. Yeah. Yeah, maybe I'll really stop to share. Yeah. Okay. Yeah.
Dominic, did you have anything more you wanted to add now?
No, but perhaps Richard would like to say something.
No, not at all. I was just going to ask if anyone else wanted to talk. How long do you usually do these conversations for?
It's in the diary for another half an hour, but you can all go home.
Yeah, we can. Whatever. Yeah.
But did you have anything prepared, Richard? Or
no? Was I meant to?
I don't know. I thought you were going to follow Maxim, but that's fine.
I followed him closely.
Okay.
Yeah. Okay. Good. Yeah.
All right. Anybody else want to?
Oh, I have actually some questions in the chat. What is it? Is it really this Asan Khan asks, is it really 1D? Yeah, eventually when we get to final number, like I don't know, solution of differential equation, WKB approximation, stuff like this, the idea is that we can write alternative form of this number is really path integral. And yeah, so in this sense, it's one-dimensional story, and wall crossing comes because it's Lefschetz symbols in complex. When you get complex holomorphic potential, sometimes they bump from one critical values to another critical values. But at the end of the day, if you translate to geometry, it will be the same as almost holomorphic disks, which we have in Foucault category.
Okay, thanks. But on the other hand, you can also consider this to be some Kähler manifold target, and I believe the function you had in the exponent was some holomorphic function on that target, right?
Yeah. I have space of maps. I have space of maps to M. It's infinite dimensional complex manifold. And we integrate kind of d minus 1 of omega over this map.
Right.
This one form. I get a holomorphic function.
Okay.
And critical points will be constant map when you fix this boundary condition holomorphic Lagrangians.
Yeah. So another sort of so you're just considering the Fukaya category of the finite dimensional manifold, but another sort of A-type construction you could do, which is maybe not what you're doing, is just consider the Fukaya Saido category of this pair.
Yes. No. It's another thing which, in principle, we should do at some point. Yeah, we have this infinite dimensional complex manifold and nice function.
Yeah.
Homomorphic function, so one can try to see what is Foucault category of this guy will be. Yeah.
Does anyone try to do it rigorously?
Yeah, I don't know.
Did anyone? I mean,
yeah, and there are more holomorphic functions. Instead of this topological theory, one can make it's actually Hamiltonian, depending maybe on time. Get huge amount of holomorphic functions with really well set of.
But part of the kind of the point was that you treat this non-existing Fukaya category, which is associated with this holomorphic potential on the infinite dimensional space, treated in finite dimensional terms if you go to these demodules. So it's like
No. I think it's really completely different game. For example, this category should get like semi-orthogonal decomposition, yeah, like
everything is infinite dimensional.
No. This will be
a finite number of vacua. I mean, so you still have I mean, this potential has finite number of critical points, right?
Yes, yeah, but for example, if consider non-exact Lagrangian manifold, this function is defined only in universal cover. And then you recover exactly lattices. You get lattice of periods. You get it will be repeated by this lattices of periods.
Maxim, here is the test. Take just complexified Chern-Simons for SLT.
Yeah. Oh, take complexified Chern-Simons. Exactly. You get you get exactly z. You get exactly z because periods will be 2 pi I. Yeah.
Nice, but now try to do it on the A model on the A side.
Yeah.
There will be some problems.
Maybe. Yeah. Yeah. Maybe it will be some problems here, definitely. Yeah. But...
Thanks.
Yeah. By the way, maybe it's a question to Maxim. Maybe you can clarify part of your talk yesterday.
Yeah.
About this Quaternion-Keller story.
No, I cannot really clarify. Actually, I was asked by Boris Pialin today. Yes. No, I cannot really clarify.
I haven't asked a question, so let me.
Okay. Yeah. Maybe
clarify what part I want to clarify. It says a contact structure for the twister.
Yeah.
And its relation to quantization.
Yes.
So they have the same number of parameters. So
you get essentially 2 Lie algebras. If we get let's say usual like symplectic torus with multiplicative symplectic form, we have this Lie algebra of Hamiltonian vector fields, which we like for wall crossing. Typically. And it has a basis identified with polynomials in 2n variables, Laurent polynomials in 2n variables. But now you put kind of extra variable on which will be not Laurent polynomial, but maybe formal power series. It will be additional 1 variable. And this could be either Planck constant. You treat like functions on quantum torus in formal expansion in H bar. You get certain Lie algebra, and the classical limit is usual. So you get this Lie algebra. If you mod out by H bar, you get usual polynomial Hamiltonian vector fields. And there's another Lie algebra maps to Hamiltonian vector fields. So the same size, you imagine like contact to n plus 1 dimensional manifold with symplectic boundary with divisor on which contact structure degenerates, and then consider contact transformation in the formal neighborhood. It will be again like function of 2n plus 1 variables.
They seem to have the same deformation. I mean, the quasi-isomorphic.
No, they're not quasi-isomorphic. They're 2 different Lie algebras, but maybe one can include them in some twistor family or something like this, and to see that then identify model space from one to another through some global holomorphic triviality or some reality condition. I don't know.
In this automorphic form, which kind of is they discover, you think that it
I think it's only just first approximations. It's first coefficients what they discuss, not really. So.
Okay.
Okay, are we ready to call it an evening, do you think?
Yeah, okay, yeah, so it's pretty late in some places at least, yeah.
In that case, let's thank Maxim very much for his contributions.
Yeah. Okay. Okay. And thank you for your interaction. It was useful. Yeah. Okay. Thank you, and see you tomorrow.
Okay.
Good night.
Night.